Welcome viewer to the first session of Module 8 on design of springs of this course machine design. In this module we will be discussing design of different springs used in the machine elements, and in this session we will be discussing the design of helical springs on the basis of strength. In this particular session, we'll be discussing design objective, stress analysis, materials for springs, and design stress. The springs are essential part of almost every machine and employed to control motion as in cam and follower arrangement. We can also apply force as in valves, clutches and brakes, to store energy as in watches, and to absorb vibrations as shock absorber. The axial force applied on the helical spring induces shear stress, torsional shear stress in the spring wire. In case of leaf spring, we apply transverse load, and again tensile and compressive stresses are induced in case of leaf spring. The complete analysis of different types of spring will be discussed in subsequent sessions. The coils of helical springs are not exactly perpendicular to the axis of the spring. So this is the axis of the spring, and the coils are not perpendicular to the axis of the spring, but they are inclined at some angle, and this inclination to the perpendicular plane of the axis is known as helix angle. And when the helix angle is less than 10 degree, we call it as a closed coil helical spring, and when it is more than 10 degree, we call it as open coil helical spring. So in this particular course, we will be only restricting our discussion on closed coil helical spring. So it means we are assuming that the helix angle is less than 10 degree. Important parameters of spring are spring wire diameter. It is here as D. Then we have coil diameter as capital D and free length as LF. So these three are the important parameters that we will be looking for while designing this spring. This is a type of extension spring. It is part of helical spring. It's a closed coil helical spring. This is example of torsion spring. We apply some load here, and this load induces basically twisting moment about the center of this coil, and that is why it is we are applying some torque on this, and these are known as torsion spring. We want that spring to fit into space available, because sometimes we generally work the spring in a very restricted space, for we have to allow for the deflection of the spring, and that is why we the stiffness in the allowable limits. So let us write the design equation of the spring, as we have discussed about the design equations in our initial two modules of this course. The design equation is sigma maximum is equal to sigma D. So depending on which type of load is there and what is the effect of the load, and accordingly we decide whether it is sigma maximum normal stress or it is shear stress. Session 1 of module 2, that we have to identify the effect of the load so that we can correctly know what type of stress will be induced in the member. So as we can see here, this spring is subjected to axial compressive load, and because of this axial compressive load on the coil, we have to identify what is the effect of this axial compressive load in the spring wire, because this load is applied on the spring. So to understand this, we have to look at this particular figure, which gives an idea about where we are applying this load. And so we can see that we are applying load at the center of this coil, and we are interested in finding out what is the effect of this load F, which is axial compressive load on the spring wire. So we have to find out at any section. We can take section here, we can take section here, we can take section here. So everywhere the effect of load will remain same. So for that, what we have already discussed, that to find out the effect of load to at some remotely located point of the member, we have to transfer this load from this point to this point. And how do we transfer? For that, we have to apply first equal and opposite force where we want to see the effect, and then we have to replace this force and this force with a couple, and this couple is this. So finally, if we see the resultant force on the spring wire, we can see that this force is nothing but the final force that will remain is this force in this direction and this couple. So value of this force is F, and this couple is F into D by 2, because the distance, this is the axial, the line of action of this force is through the axis, and it is here the perpendicular distance between these two forces is this, and that is equal to D by 2. We can see this coil diameter is given by this. In plane shear force induced in plane shear stress, and this twisting moment, because this is the moment acting in the plane of cross section of spring wire. So this is the plane of cross section of spring wire. This moment is acting in the plane of cross section of the spring wire, so that is why it will induce twisting. Those who want some more knowledge on this, how we are doing it, so you can see the second session of module 2, and the link is given in the description. So in plane shear stress will be uniform throughout the cross section of the spring wire, whereas the uh, torsional shear stress will have this distribution. So we can algebraically add these two, and finally we get the resultant of this, because it is both these are in opposite direction. Here we have the stress is in same direction, so here the effect will be reduced, and here the effect will be maximum. And note that this is the outer fiber here, and this is the inner fiber here. So it means the stress in the inner fiber of the spring wire will be more as compared to outer fiber. And to write design equation, we know that design equation for this, because it is only shear stresses are induced, so we will be writing tau maximum is equal to tau d. So this left hand side will be obtained using this sigma 1 plus sigma 2 maximum, and right hand side as usual we will be having strength over factor of safety. And strength in this case of shear stress, we will be using SYS divided by factor of safety. And from where SYS is to be obtained, that will be seen later. Now we can substitute the values of the tau 1 and tau 2, because tau 1 we know it is nothing but the load divided by area, that is load is F and area of cross section is pi by 4 d square, and tau maximum is nothing but it is mt by j into R maximum, and R maximum is nothing but capital D by 2. So this is the point of maximum stress, whether you write here or here, the tau 2 maximum will remain same, but we will be writing tau 1 plus tau 2 to get maximum tau maximum to fit into our design equation. So after substituting, we get this expression, and this factor is known as stress multiplication factor, and the new term C is known as spring index and given by d by t. The common generally used values of spring index from 4 to 10, we can take general range from 4 to 10. It can be in decimal, it can be in fraction, it can be sometimes less than this and sometime more than this, but in general we take it, if we have to assume, we have to assume between this. But then again, for on the basis of certain justification, because when value of C is more, it means coil diameter is more, so we need more space to fit this spring, and when the C is less, the coil diameter is less, and we may require less space. So depending on the space availability, we decide what value of C should be used. And Ks, as usual, we have just discussed this. Ks is the shear stress multiplication factor for spring. And then this particular expression that we have used, it's only for we have derived this torsion equation for shaft which are of uniform length. Both the fibers are of uniform length, inner fiber and outer fiber. But in the case of spring, we have the complete curvature around the coil, and we have the different lengths of fiber, inner fiber and outer fiber. So in this case, let us say this point is A on the outer fiber, and this B is arbitrarily taken point at some distance from A, and the corresponding the points on the inner fiber is C and F. So for equal amount of twist, we have the length, because if even if we take, suppose this is my spring, and here we have point A and here we have point C. So when we apply some twisting moment on this spring, this A may be twisted to this point and C may be twisted to this point. So for a particular cross section, whether a point is lying on outer fiber or inner fiber, the angle of twist will remain same. So angle of twist will remain same whether it is inner fiber or outer fiber. So shear strain, but shear strain will be different, because shear strain is angle of twist divided by the length of the fiber. So that is why the strain in the inner fiber will be more and the strain at the outer fiber will be less, because of the differential length of these two fibers. So it further increases, because strain is more, shear strain is more, it will increase the shear stress. So shear stress here, when we use this formula, this we assume that the inner fiber and outer fiber both are of equal length, and because of this curvature, the stress will further increase, and this is given by, the stress is given by K times this KFD by pi dq, where K is known as Wahl's correction factor. And this was by scientist who first introduced this correction factor for calculating stress in spring, where K is given by Ks and Kc. Kc is the curvature factor, and K is given by 4C minus 1, 4C minus 4 plus 0.615, and this factor is given by Wahl's. So now we can substitute these in design equation, and finally we get design equation as this. So this would be our design equation that we'll be using for designing spring. And shear stress, design shear stress tau d, that is on the right hand side, is given by this, that is SYS, shear strength divided by factor of safety. So let us now focus on the design stress, how the design stress is obtained. So because in case of spring, we generally deflect spring too much, and we want, and that deflection should be within the elastic limit. So the energy that is stored is known as, per unit volume is known as modulus of resilience. So we want that spring material should not plastically deformed when it is subjected to load. So it means that modulus of resilience of the material should be more, and a material with larger value as SYT and lower value of E is suitable for spring, so that the modulus of resilience is more. So plain carbon steel, in 4 different grades we use plain carbon steel: grade 1, grade 2, grade 3, grade 4. Grade 1 is for light service case, and it is for safety valve, and that is again low stress average service case as in governors, and high stress average service case as in suspension, automobile suspension, and this is for severe service case. So these four cases have been introduced here: the light service case, low stress, the average service case, and then it is the severe service case. So these service cases are related or linked with the number of cycles that a particular member is likely to be subjected during its life. So light service case is up to 10 to the power 4 cycles, and the average service case is for 10 to the power 4 to 10 to the power 6 number of cycle, and severe service case is 10 to the power 8 6 greater than 10 to the power 6 number of cycles. So that is how we can select a spring, a material for spring, if we are looking for plain carbon steel. We can use unalloyed oil hardened and tempered steel for again this steel is in two grades. One is spring steel wire SW, another is Wahl spring wire. This is for fluctuating load generally used, and up to temperature is 100 degrees Celsius, and if it is more than that we can go for Wahl's spring fluctuating load with temperature more than 100 degrees Celsius. Then alloy oil hardened and tempered steel for elevated temperature. Then stainless steel we use for corrosive atmosphere. So all these spring related material and their properties are given in standard, and we can these are available in the design data book in this form. So for plain carbon steel we have this type of table available in data book on page number 194, and table number is 14.4. Here interesting thing that we have to note is in the first column we have wire diameter, and then we have ultimate strength for different type of springs. So this is not that clear, but we have to bear with it. I'm trying to explain so that it is easily understood. So it is grade 1, grade 2, grade 3, grade 4, and then so on. And the ultimate strength, if you see it, reduces as the diameter of wire increases, and this is because the larger size of wire diameter means there are more chances of flaws and defects, so that reduces the ultimate strength of the spring wire. Now everything is given in this IS standard, that is 4454201. You can Google it. It is in 3 part that is available or suggested by the Indian Bureau of Indian Standard, BIS, and this is the number. So using this SUT, we can find out SYT as 0.75 times SUT. Then again, this is from the standard, and SYS is 0.577 times of SYT, that is according to distortion energy theory. The factor of safety we take 1.25 to 1.5, and this design stress we can obtain as SYS by N. Here very one you may ask one question, that why this low factor of safety we have selected, whereas the importance of this spring is very high in the machine. So this is because we have tested spring wire for the different sizes of spring wire. It is not the general material we have tested. We have SUT for different wire size. Actual wire is tested. When we test actual wire which is to be used for manufacturing, the actual component, in that case the lower factor of safety can work. But according to BIS, we can also use directly tau d as 0.5 times of SUT rather than following this complete process or steps for 3-4 steps, we can directly write according to BIS. We can take tau d is equal to 0.5 times of SUT. So this is about the plain carbon steel design stress. If we are selecting the spring steel material, in this case the data which is available to us is general. It is not given in form of not given for different wire diameters. So it is given in general, so that is why we have different concept or different concept we have to apply for calculating design stress. And SYS in this case is taken as 0.5 times of SUT, that we get it from here. For light service case, we calculate tau D dash as 0.8 times of SYS. For average service case, we further reduces the design stress, and for severe service case, we further reduces the design stress. And then it gives us the effective value of, not effective, it gives us the theoretical value of design stress. Now we have to use the factor which is for known as B factor or the size factor. This B is size factor, and this factor is given by this. B is equal to 0.86 plus 1.75 D, and B is this. So this is for D greater than 12 mm, and this is for D less than equal to 12 mm. So these are the steps that we have to follow for alloy steel. So this is for alloy steel or spring steel or the steel material where we are not given the ultimate strength for different material, and this is for plain carbon steel, or in other word we can say this is the uh, design stress of steel of spring material where the ultimate strength is given for different diameter of the spring. So thank you very much for this session. Please subscribe, like and share if you like this video. Thank you.